Welcome to the North Pacific Garbage Patch, the largest human trash dump in the world. Spreading across the Pacific Ocean, the North Pacific Garbage Patch is really more of a series of trash vortices and is the top vacation destination for plastic, chemical sludge, and wood pulp. Defining its size is difficult because it's always moving and it's mostly a soup of tiny microplastics, not an island of grocery bags and drinking straws. But some scientists estimate it's approximately 700,000 square kilometers, which is roughly the size of Texas. Actually, it's one of 5 giant collections of trash circulating in oceans all over the Earth. If you've spent time on beaches, you might have noticed plastic trash like water bottles and toys, but there's so much almost invisible junk too, like small beads or tiny slivers. Each beach around the world has this plastic pollution because of how trash moves from inland to the ocean and then gets caught in ocean currents. Whether you live on a coast or not, everyone is connected to global ocean currents circulating tremendous amounts of energy and trash. I'm Alize Carrere, and this is Crash Course Geography. Somehow, trash can show up on a beach in California from a pot of trash 2,500 nautical miles away east of Hawaii. That's so far for one speck of plastic, or even a whole water bottle, with or without the secret message, to travel. To get there, it all starts with the wind. In our last episode, we explored how the horizontal movement of air, called wind, moves in predictable directions and creates the general patterns for global circulation. In the oceans, we call the horizontal movement of water an ocean current. Like the winds, ocean currents are basically rivers of energy moving in a persistent and predictable direction. And also like the winds, ocean currents are driven by differences in density and pressure. In the air, density and pressure changes come from differences in the amount of insolation, or incoming solar radiation, that different parts of the atmosphere receive. And ocean water is heated by insolation too. Because of how much direct sunlight it gets, water closer to the equator absorbs more heat energy than water at higher latitudes. This creates density differences within the ocean because, just like air, warm water is less dense than cold water. Basically, when heated, molecules like to spread out. Water density is also affected by salinity, or the salt content of the water. Saltier water is more dense than less salty water because there are more molecules of salt and water hanging around. Warmer water in the ocean expands just like air, but because it can't expand sideways, because there's already water there, it expands up, elevating the surface just slightly, like a hill. And colder or saltier water contracts, lowering the surface into a depression. So the ocean's surface isn't perfectly flat. It contains sea surface height anomalies. A hill of water exerts extra pressure compared to a dip in the sea surface height. And in general, whatever's in a high pressure area, whether it's air or water or a student in a stressful class, wants to move to a low pressure area. So these pressure gradients force the water to flow around the globe. Technically, it's all the same water, but separate currents are defined because they consistently move in the same way, kind of like different highways of water. There are actually 30 major named surface currents and dozens more smaller currents transporting ocean water around the globe. So if our trash found its way to the right spot, it could travel the world. We can draw lots of comparisons between ocean currents and wind patterns, but surface currents are also driven by strong and steady streams of wind. Energy is transferred from the winds to the water through friction as air blows across the surface. For example, the winds that result from subtropical high-pressure areas around 30 degrees latitude also help create the ocean currents that circulate there in patterns called gyres. But even though ocean currents generally follow the winds, the two aren't mirror images. Ocean currents come up against huge roadblocks that air blows right over. Continents and large land masses. These roadblocks give currents irregular shapes, especially in places like the Indian Ocean, the Arctic Ocean, and the northern Atlantic Ocean, where there's lots of land. Currents are also curved by the Coriolis effect, like all fluids on the Earth's surface. Remember, the Earth is rotating fastest at the equator and slower as we move towards the poles. So if something that's not directly connected to land moves north or south, the change in momentum causes its path to bend. The Coriolis effect can actually deflect some surface currents, depending on where they are on the globe. Like, as currents move away from the equator, the Coriolis effect gets stronger because the Earth's rotational speed rapidly slows down and can break up currents into chains of lots of circular vortices, or eddies. These get smaller the closer you are to the poles as the Coriolis effect bends the currents ever more tightly. Then, as the Earth rotates faster as we move towards the equator, the Coriolis effect gets weakest until it's basically non-existent exactly at the equator. So equatorial currents aren't deflected right or left. Water can simply flow in a straight direction pushed by the winds. So if we look at the circulation map, most of the surface currents making up gyres don't cross the equator, but flow along it horizontally. Then it's the combined forces of winds and the Coriolis effect that causes gyres to flow in a clockwise direction in the northern hemisphere and a counterclockwise direction in the southern hemisphere. But let's go back to the idea that ocean currents not only run into stuff like land, they can also carry more stuff than wind. Maybe they're a highway for eel migration, or they play a role in a water bottle's journey from a store shelf to the North Pacific garbage patch. At some point, this bottle got snagged in the North Pacific Gyre, which is really 4 currents that follow how the air moves around the northern subtropical high pressure area. To imagine its journey, let's go to the thought bubble. Let's say our water bottle fell into a municipal storm drain in Hawaii that got flushed into the Pacific Ocean. Starting at the equator, the trade winds drive water west in a flow called the equatorial current. This carries our water bottle to the eastern coastline of Asia, where warm waters pile up against the land. So the warm, energy-rich waters are deflected toward the North Pole, pushed by both pressure gradients and the Coriolis effect that balance each other out. They flow into the Kuroshio Current, moving north along the Asian east coast, where our bottle could wave at the Philippines and Japan. You know, if water bottles had arms. As it reaches the latitude of the westerly winds around 35 degrees north, the current begins to wobble more, and along with our bottle is pushed eastward and separates from the coast. This forms the North Pacific Current, bringing warm waters to the southern coast of Alaska. And then, land ho! Eventually, our water bottle encounters the west coast of North America and is deflected back towards the equator, moving from British Columbia, Canada, to the Baja Peninsula in Mexico. This California current is cold, having released the warmth that the water was holding in the equatorial and Kuroshio currents. If the bottle manages to stay in the gyre, it could float on through those warm and cold currents for years, traveling through clear moonlit nights and rough typhoons. Because our bottle is a processed plastic, bacteria don't eat away at it. But wind, waves, and sunlight have broken it down into microscopic particles, so all that's left is a bead that ends up floating in the North Pacific garbage patch. Thanks, Thought Bubble. Wind-current interactions are actually much more complicated than just winds pushing water around, and it's an area oceanographers are still trying to understand. For geographers, we're concerned with how stuff gets moved around the globe. There are actually 5 major gyres in the world, including this North Pacific Gyre, each with its own garbage patch. And they all follow similar patterns, with warm currents bringing warmth and humidity to the continental east coasts, and cold currents moderating temperatures and having a drying effect on the west coasts. Ocean circulation in the southern hemisphere is similar, except that the gyres flow in a counterclockwise direction. And because there's very little land poleward of 40 degrees south, the Antarctic circumpolar current, or west wind drift, circles around Antarctica as a cold current, almost without interruption or directly interacting with the warm equatorial waters. Surface currents generally move warm waters poleward and cold waters toward the equator, so they're important regional air temperature regulators, in addition to moving anything that happens to be in the ocean, from schools of fish to bits of plastic. But surface currents don't make up all of the horizontal motion of the ocean. To see the rest, we have to go deep into the ocean. Deep currents travel at slower speeds beneath the surface currents. They move ocean waters both horizontally across the floors of the world's oceans, but also vertically from the ocean floor to the bottom of surface currents as part of Earth's thermohaline circulation. Just like surface currents, deep currents flow from high pressure to low pressure. Even at these crushing depths, slight pressure and density differences are also caused by temperature and salinity changes. For example, the more salt content the surface water has, the more dense it is, the more likely it will sink as it reaches the poles. In some places, that water will sink up to 2,000 meters to where deep currents flow. A complete circuit of a deep current may take up to 1,000 years. Even still, deep currents are critical to the movement of nutrients around the world. Many fisheries, for example, depend on cyclical upwelling of nutrient-rich water moving from deep currents into local surface currents. While nutrients released through decomposition near the ocean floor are pulled up by upwelling, oxygen cycles down from the surface to the deep, which keeps those decomposers and other deep-sea organisms supplied with oxygen for respiration. So the broad global circulation of deep currents is like a vast conveyor belt of ocean water that brings warmth from the equator to the poles, nutrients from the floor to the surface, and oxygen from the surface to the floor. Marine habitats near upwellings only cover about 1% of Earth's oceans, but account for up to 50% of the global fish harvest. At least 1 billion people rely on fish for their primary protein, so deep ocean circulation not only moves energy around the globe, but also helps create the conditions that feed a large part of the world. Higher up, dominant winds and surface currents have helped move people around the globe for thousands of years. With the movement of ships has come the movement of people and the things they deem most important. We can understand the material culture of a people by the marine debris they create. Some of that trash will get swept into regional surface currents like gyres, but some will get caught by smaller local currents and wash up on the shore without having traveled the world. Like, there have been outbreaks of whole toys washing up on beaches, from rubber ducks to Lego dragons to Garfield phones. What do all of these things have in common? Well, like you've probably intuited, marine debris in the 21st century is mostly plastic. There are 8 million metric tons of plastic bits and debris that we don't know the origin of, or non-point source pollution, that's estimated to be in the oceans, but there's also bigger garbage out there too. Take that whole Lego dragon. It didn't travel far. It came from a wrecked shipping container that fell into the ocean after a huge once-in-a-100-years wave hit the cargo ship that was carrying it. In fact, there are thousands of shipping containers each year that fall off cargo ships due to rough weather or other mishaps. This map shows the movement of the 50,000 ships each day moving goods around the globe. Some estimates say 90% of global trade involves container ships crossing the oceans. But as ships move, they're emitting air pollution that rides on global air circulation currents through the atmosphere, or dropping stuff that contributes to ocean pollution. These types of pollution can't be linked to a particular ship because air and water cross political boundaries. In fact, those plastic beads and dragons on the beach represent how we're all connected by the global circulation of air and water, and how garbage patches won't clean themselves. Our global economies depend on the circulation of goods moved by ships, and local economies depend on the circulation of nutrients that create rich fisheries, all of which leverage the dependability of ocean currents. So who's responsible for cleaning international waters, and how do we balance our societal needs with protecting the planet? There aren't easy answers, and there might be rough seas ahead. In fact, I see some clouds on the horizon.